All right, so in this example, we're going to go ahead and use a different graph, the square root of x, just to kind of change things up a bit. We have compare each graph with f of x. So in this case, our OG is going to be, remember OG is our original graph, is going to be f of x equals square root of x. We have three different graphs. So what I'm going to do, or functions, what I'm going to do is I'm going to go ahead and define here on the side what the transformations are, and then we'll go ahead and graph them, okay? So for the first one, h of x is equal to negative square root of x. We have a negative in the front. So remember that a negative in the front is like saying negative f of x, okay? Where we make the entire function negative, so all my values are going to jump over to the bottom of the x-axis. So this is just a reflection over the x-axis, okay? So let's go ahead and graph that, and then we'll come back up to letter B. So here are my three graphs, and this is the graph for letter B. Again, ignore this stuff for now, okay? We're just going to focus on the graph. So notice I did go ahead and draw our OG for square root. I only included, well, kind of sort of 3 points. You have your 0, 0, 1, 1, and then 4, 2. I know that those 3 points for sure are on square root of x. If you're not sure about how to do the OG, guys, all you got to do is graph it and check to make sure that it matches whatever you think it is, okay? So here we go. We're going to go ahead and reflect. That means that this point stays in the same because 0 is just 0, okay? This guy, instead of being here on the top, it's going to jump over to the negative side. And then my point here, 4, 2, is going to jump down to 4, negative 2. So it looks like this graph is something like this. Okay, and this new one would be our h of x. In function notation, we would have h of x is equal to negative f of x. Okay, ignore this. I really need to get some white out. I just haven't gotten around to it, so pretend that's not there. Letter B, we have h of x equals, I don't know, b. That way it's a different letter. So b of x is equal to the square root of negative x. So just like the one and a few examples back, okay, when we have a negative on the inside, this is like saying f of negative x, okay? So that means we're going to have a reflection over the y-axis. Okay, so we're going to go ahead and do the same thing we did for letter A. Here is letter B, the graph. So the points I already have here, I'm going to flip them over to this side now. So 0, 0 again stays there. This point, instead of being 1, 1, it's going to be negative 1, 1. And then negative 4. Let's see, 1, 2, 3, somewhere over here, 4, 2. So this one looks kind of like this. Remember, this is just a sketch, so it doesn't have to be perfect, but you have to have the general idea of where it should land, okay? So this would be our b of x. In function notation, okay, so I'm going to kind of squeeze that in here. B of x is equal to, okay, equal to, well, it's just f of x, right? But with the negative on the inside. Okay, and last but not least, we have this one up here, which is our y equals. Hopefully you can see this is supposed to be a negative. Okay, there's a negative here. If you can't see it, I can rewrite it. Y equals negative square root of x plus 3. This is the same thing, okay? So for this one, it looks like we have two things going on, okay? We have a negative on the outside, so I'm going to put that negative out here. And then we have this plus 3 on the inside. Now, square root, it kind of acts like our parentheses, so this would all be inside the parentheses, okay? So two things. We have reflection over, since it's in front, okay, it would be like the first example, so over the x-axis, okay, comma, because there's another transformation, 3 units, I'm going to say, since it's a plus 3, remember you think opposite, so 3 units left. Okay, so here's our graph for that one. It's a little bit squished here. Hopefully you can follow. We have a reflection and 3 units left. So here's this point. It's going to flip over. So it's kind of right here. This guy is going to flip over. So somewhere, let's see, right here. So, and this is our, I'm going to put like a little dashed line first, curve. This is our reflection. And then from here, we have to go 3 units back. So 1, 2, let's see, 1, 2, 3, somewhere right here. Okay. This center point I also have to move. So 1, 2, 3. So there it is. And then finally from here. So let's see, 4, 1, 2, 3, something like that. So it looks like this graph is something like this. And you can always check these, of course, with Desmos and your Inspire, or not Inspire, I'm sorry, 84, 83. Just make sure that you are able to describe exactly what happens and be able to go backwards, okay, like the example before, okay? And that is it. This would be our, what was this? Y. This is just Y. So Y equals negative F parentheses X plus 3. Basically, this is just matching what I already wrote up here, okay? And that is it, guys. One more, I think one more example, maybe. Is it one more? Oh, we have a few more. I'm sorry, I lied. I'm sorry. So example number 5. What are the domains for example number 4? So let's just, this should not be too bad. I'm just going to go ahead and define what the domain is. So for letter A, we have from 0 to infinity. Okay, 0 is included because there is a point there. For letter B, we have the opposite. So this guy is going the other way. So we have negative infinity to 0. Okay, and for letter C, we started a different point on this one. This looks like it's going to be negative 3. Okay, so this would be from negative 3 to infinity. There's a note I want you to take note of at the bottom, and I actually put it as a remark. It says, remember that when sketching graphs of square roots, so that's what we just did, we need to restrict the domain. And the reason we need to do this is because we cannot take the square root of a negative number. Now be careful here because notice that this guy does have negative numbers, and so does this one. But the only reason we can include them is because we transformed our original graph to something else, where you can see plainly that there's going to be negative numbers on this side, and there's some negative numbers in this part right here. So just be careful with that, okay? That's it for this one. Almost done. I believe this is the last page. We have non-rigid transformations. So the transformations we just discussed right now, you can copy this as I'm speaking, were rigid transformations, meaning that all we do is kind of move them left, right, up, or down. We're just translating the position of the graph. We're not really changing the dimensions or anything like that. Non-rigid transformations does exactly that. It makes the graph thinner or wider. We used to call these vertical stretches, vertical compressions. We also call them narrower and wider. So just some old vocabulary we're bringing back in here. What happens is we take a number, any number really, and we can put it in front of the function like so, and we can put it inside with the x to be multiplied. If we put it in the front, okay, like this one, then we're going to have a vertical stretch by whatever that number is, by a factor of c, okay, if it's greater than 1. If this number is between 0 and 1, so and I went ahead and put the absolute value because if it's negative, you have a double transformation. So just think of it like if it's positive and it's between 0 and 1, okay, then it's going to be a vertical shrink. This is also known as a vertical compression. So you have seen this before. The one you have not seen is probably this one. This is if we go ahead and multiply a number on the inside. So if we multiply a number on the inside, you're thinking kind of the opposite, okay? So if c is greater than 1, you think it's going to be opposite of this one. So it'd be horizontal shrink or compression. So you see how the words just literally, they're opposite of each other. If it's going to be between 0 and 1, then now we have a horizontal stretch. So it's the opposite of whatever you're going to have up here. And we'll see an example for that. Okay, so here we go. Compare these graphs with f of x is equal to the absolute value of x. So just like the ones before, I went ahead and drew our OG for each example. We're going to go ahead and take a look at each one. We have that h of x is equal to 2 times the absolute value of x. So in this one, our c value looks like it's in the front, okay? So that means that I'm going to have a vertical stretch. I'm just going to put by 2. You can put the by a factor of it. Because of my space, I'm going to just put by 2. So that means that this graph is going to get vertically stretched. So think of it like this V right here is going to get stretched. So if I pull it up, it kind of gets like thinner, okay? You're pulling it up like this. All right, so what's going to happen is the 0 will stay the same because it's just 0, okay? The next ones are going to get multiplied by 2. So one way to think about it is what I used to teach my algebra 2s last year. I said, well, pretend this is kind of like a slope, okay? The slope of the OG is 1 because it's up 1 over 1, up 1 over 1. The slope of this guy is 2. So we're going to go, instead of going up 1 over 1, we're going to go up 2 over 1. So 1, 2 over 1. 1, 2 over 1. My graph's a little crooked, but that's all right. But what you want to do with the absolute value is put it on both sides. So up 2 over 1. And I really just want these points here. And this represents h of x. And you can see that it looks like it's thinner than the original. And the reason that is so, again, is because we are vertically stretching the OG. We're taking this V and we're stretching it upward vertically. So that's why it looks like it's kind of squished, okay? For our function notation, okay, this would just be h of x is equal to 2 f of x. Because all we're doing is taking the 2 and putting it in front of our function. Next one. Now we have g of x is equal to half times the absolute value of x. So now we're kind of thinking slope-ish of 1/2, which means that instead of going up 1 over 1, okay, we're going to go up 1. So let's put our first point, 0, 0, up 1 over 2. Same thing on this side. And you can see that this graph looks a lot wider. Yours is a little bit better than mine. Okay, it looks a lot wider. And that the reason that is because this is actually a vertical shrink. Okay. So by definition, from what we wrote on the top, if this number here is between 0 and 1, which it is, you should have a vertical shrink or compression. If you prefer to use compression, you can. Because I know that that's what we mostly used last year. By 1/2. Okay. For our function notation, we would have g of x is equal to 1/2 times f of x. Okay. And that is pretty much it, guys, for that one. The last one I want to go over is that tricky one with where the numbers on the inside. Okay, and I wanted to do this one specifically so you could kind of see how they relate. So here we have another function, kx, okay, is equal to f of 2x. So notice that this right here is actually our function notation. So I'm going backwards on this one so that we can see how it works. So that way you know how to go from here to the next one. So I'm going to go ahead and rewrite this now as, we'll use this color, as kx, okay, because that's the function, this one, is equal to, and instead of f, I'm going to actually use what it's equal to. Remember that according to our example, this is the absolute value of x. So it would be absolute value of 2x. And this is our function that we're looking at, okay? Now these are a little bit tricky because you're thinking, according to what I have up here, okay, this would be a, let me see, where does that fall? So it's here on the inside and it's a 2, so it would be greater than 1. So it's going to fall under this category, horizontal shrink by a factor of 2. So let's write that down first, okay? This is a horizontal shrink or compression by, by 2. Okay, so for these, you have to think about it like your values are kind of getting squished inward. So you're think an accordion. Okay, so an accordion would be like, horizontal. And when you squish it, when you're playing an accordion inward, this is actually going to get closed this way. So it actually looks really similar to this guy. Okay, but if that's hard to imagine, which you can do, which I tend to do with these, is actually just make a table so we can figure out, well, what are some of the points I'm going to use. So I'm going to go ahead and do that. I'm going to do x and then k of x right here, which is equal to this right here. Okay, and I'm going to pick 3 points that I know are going to be easy to find. So I'm going to pick -1, 0, and 1, because those are probably going to be easy for me to calculate. So for 1, we would have k of -1 is equal to the absolute value of 2 times -1. 2 times -1 is -2, but the absolute value of -2 is 2. So that first point that I have to plot is -1, comma 2. So here we go, -1, comma 2. So there it is. Okay. 0 is going to be nice and easy because anything times 0 is just 0, right? So 2 times 0 is just going to be 0, which is 0. So this one stays right in the center. And last but not least, k of 1. We're going to plug in this 1. So 2 times 1 is just equal to 2. Absolute value of 2 is 2. So this point is 1, 2. So 1, 2. Okay. And we can go ahead and connect at this point. And notice that it actually looks almost identical to the one on top, which kind of tells you that these two relationships are actually kind of the same thing. We give them different names because it depends on where that function is. I'm sorry, that C is located. So we want to make sure we understand the different terminology. Okay, so horizontal shrink, vertical stretch. In this case, in this particular example, same outcome. And that is it, guys. That's it for this. If you have any questions, as always, let me know.